Hi, welcome to this session. We're going to answer some problems about magnetic fields of moving charges. And the first problem is about a cable that has an electric density that changes depending on the radius. And the way it changes can be measured by J R, J, remember, is the density. It's equal to J0 multiplied by the radius R over radius, the whole radius. So what does that mean? Well, J0 is the maximum charge density. R is the place where you will be located. So that if you're trying to put a ring in this part, then you would have radius R, and the radius, the big R would be this circumference. So that if we locate ourselves just at the center where the radius, the small r, it's 0 because it's just a dot inside, then J would be 0. And if we locate it at the same point at the circumference of the whole wire, then we have a maximum J0. So that we know that as you go from the inside to the outside, the amount of charge density that you're containing will be increasing, and that makes a lot of sense because it's like if you put yourself in the center of a cake and you just put a straw inside like that, and you take it out, then the amount of cake that you will have is just like the radius of the straw. And then if you grab the whole cake like that and you lift it up, then the amount of cake that you will have is the whole cake. So okay, that's the explanation. I'm gonna write just here the constant and how it will be changing depending on the radius. And so the problem is asking how an equation where we can find what's the magnetic field, because they're not asking about the charge, they're asking about the magnetic field inside the wire and outside the wire. So we know a lot of things about wires and we know a lot of things about current, and one of the things we know, and it's because of the Ampere law, is that if we grab an enclosed surface of a wire, then we can see how many charge we have enclosed, and then we can measure the amount of magnetic field that we have. And that equation is this one. The integral of the magnetic field times ds, that is the differential of surface, it's equal to the permittivity. We use, I'm gonna make a small pause here because maybe you don't remember what's permittivity. In permittivity, it's how easily it's for the electrons to flow in a given space. And this mu0, it's the permittivity of vacuum, and that's a constant, and you can find that on Google. And so that we have this permittivity, and that would be multiplying the enclosed charge. And we know also that the enclosed charge is equal to the, I know that, but I can't find it. Enclosed charge. Where is it? Oh, yeah. Yeah. Okay. So that the charge is equal to the integral of the charge density. Makes sense? Like you have a charge density and you just want a small part of that, and that will be multiplying the differential of area. And well, we know that the area, because I'm going to draw it here, that'll be our whole wire. This is R, and then we're locating small r over here. And well, the area is basically it's equal to the integral of, well, from 0 to r from then j, we know from here that when we're using the radius, we have j0 times r over radius, and the differential of area, it's basically the differential of perimeter times the radius, well, times the differential of radius, and so we have 2 pi r times the r, and that will be our equation for the current. And we also know that that can be solved like taking outside every constant, and we would have something like, wait, I have that over here. That's 2 pi j 0 times r, because I took outside 2 pi and r and j0, and that'll be multiplying the integral of r only, and that'll be r like that. Okay, and that'll be evaluated from 0 to r, and that's correct. And well, as we have r and r and 0, you know how to solve that, so we can just erase that, and we've got ourselves on an equation. And well, that equation can be applied to this, because we now know that, well, I'm going to erase all this. Sorry about the space, but that light, that thing, doesn't let me write like in that space. Or, well, going back, then we have with this part of the equation, we know that as BS and B are parallel because of the right hand rule, then we also knew that the current was flowing this way. So if the current is going this way, like over, pointing towards you, then the magnetic field would be going that way. So this would be B, and DS will be parallel to B, ds. So as they are parallel and we have a dot product, then well, first we can take outside the b, and the differential of surface, it's basically the equation for the perimeter. So that's 2 pi r, and okay, and we know that the enclosed surface is, this is just j times, well, the integral that we already solved, times the, it was times the, well, no, it was just j, like the j that we solved. So got mu 0 times all of this, two pi j 0 reduce cubic times 3r, and oh, my mistake. This r, that's a big R because that was a constant and not a small r. So we got something like that, and well, we can start eliminating. So our equation for the magnetic field inside our wire is just mu 0 times, no, this is out, times j 0 over 3r times r squared. And that's the correct response. And so you can save that, and that we now know, well, they're now asking what's the magnetic field outside the wire. And I don't know if you remember this, but as you go far away from the wire, the magnetic field will be reducing. And so we'll see if that happens here. As the field, it's still the same, we can say that the left side of our last equation will keep the same. So we have the field times 2 pi r, that's field times the differential of surface. It's equal to mu naught multiplying our current enclosed. And in this case, our current enclosed will be equal to, well, you remember our last solving of the integral? We had something like, it's 2 pi j naught over r, big R now, times r cubic over 3. And now we'll be evaluating from 0 to r, big R, that's the radius of the whole cylinder. Remember the cake? We now grab the whole cake, and so we would have 2 pi j naught radius, no radius, over 3 times radius squared. And that be just the current. So we have 2 pi j 0 r squared over 3. And if we solve for B, that's the magnetic field, then we have the 2 pi goes away, mu naught j 0 r squared over 3r. And we remember that big R is the whole cake, and R is the radius of the of the straw or the thing you grab the cake with. And well, in this case, R should be bigger than the cake. And here, if we increase R, because R is inversely proportional to B, because it's yeah, you know that. And so if we start increasing R, then B will be decreasing. And in the last one that I don't have over here, yeah, I have it outside, inside, we got B equals 2 pi J0 R cubic over 3R. Well, here, as the radius is directly proportional to B, then if we increase the radius, then B will increasing too. And that's all.